Have you ever stopped to think about how your messages, your bank details, pretty much your entire digital life stays private? Well, it's not magic, it's math. And in this explainer, we're going to pull back the curtain and see how a few really elegant mathematical ideas come together to create this virtually unbreakable digital lock that, protects our world every single day. Let's dive in.
So this is the big question, right? This is the fundamental challenge of our connected age. The internet, for all its wonders, is basically a public square. Every single piece of data we send, from a quick text to your credit card number, is by default like a message written on a postcard. So how on earth do you send a secret when you know the mail carrier and literally anyone else along the route can just read it?
I mean, really think about it. When you send an email or visit a website, your data doesn't just go from point A to point B. Oh no, it's more like a pinball, bouncing between all these different servers, routers, and networks all across the globe.
Every single one of those stops is a potential eavesdropper. Without some kind of protection, your postcard is totally on public display. So the solution isn't a better envelope, it's a secret language, a language that only the person you're sending it to can understand. What we need is a lock, one forged from the very laws of mathematics itself.
Okay, so the solution comes from this beautiful concept in math known as a trapdoor function. You can just think of it as a one-way street. These are mathematical operations that are incredibly simple to do in one direction, but are fantastically difficult. We're talking nearly impossible to reverse.
Here's a great way to think about it. Imagine mixing two different colors of paint. It's super easy, right? You just swirl them together and boom, you've got a new color. But what about trying to perfectly separate that new color back into its original two? It's impossible. You can't do it. And that is the core idea of a one-way function.
Now, here's the digital version of mixing that paint. It's called prime factorization. A computer can multiply two gigantic prime numbers together in a fraction of a second. But, and this is the important part, if you only have the result, that number n, trying to work backwards to find the two original primes that made it, well, that's one of the hardest problems in all of mathematics. That difficulty, that giant computational wall, that's the secret to our lock.
So to actually build our lock, we need one more tool from our mathematical toolkit. It's called Modular Arithmetic, but don't worry, you can just think of it as clock math. See, instead of a number line that goes on forever and ever, we're going to work inside a closed loop, where the numbers just wrap around, exactly like the hours on a clock.
For example, on a 12-hour clock, 14 o'clock is really just 2 o'clock. In clock math, we'd say 14 is the same as 2. Now, what's so critical here is that this operation intentionally loses information. If I just tell you the answer is 2, you have no idea if my original number was 2, or 14, or 26, or whatever. And this is how we hide the original value right out in the open.
Okay, this one looks a little intimidating, I know. But trust me, this is the secret passage. We have our one-way street, right? But how does the person you actually want to read the message get back to the start? Well, they need a hidden shortcut. And Euler's totient function is this brilliant mathematical key that creates that secret path.
And here it is. This is the magic. While the function itself might seem really complex, how we use it here is incredibly elegant. If you know those two secret prime numbers, p and q, you can use this simple little formula to find a special number. This number is the trapdoor. It's the key that makes reversing our one-way street totally trivial for you, but it stays impossible for absolutely everyone else.
All right, so let's recap. We have our one-way street thanks to prime numbers, we have our clock math to hide the values, and we have our secret trapdoor key from Euler's function. Now let's put all these pieces together. It's time to actually forge the lock and key.
So here it is, the basic recipe that secures trillions of dollars around the world every single day. First, you choose two enormous secret prime numbers. These are your personal secret ingredients. Then, you multiply them together to get n, and that's a public number you can share with the whole world. But here's the real magic. You use your secret primes to calculate that trapdoor number, which in turn lets you forge a unique, private key that only you can ever have.
What this whole process creates is a pair of keys that are mathematically linked. The public key is kind of like an open padlock that you can give to anyone at all. They can use it to lock a message in a box, but once it's locked, only one thing in the entire universe can open it, your private key. This is exactly what's happening every time you see that little padlock icon in your web browser.
And what's really cool is that this system does more than just hide things. It actually proves who you are. Because the keys are such a unique pair, locking something with your private key is like signing it with a signature that is impossible to forge. So when your bank gets a transaction request, this math proves it was you and only you who could have possibly sent it. The math itself becomes the witness.
So this system seems pretty perfect, right? Unbreakable. But the story doesn't end here. The security of our entire digital world, we're talking our banks, our messages, our very identities, it all rests on a single massive bet that our mathematical one-way street will always be a one-way street.
This leads us to the million-dollar question, and I mean that literally. There's a prize for solving it. It's one of the biggest unsolved problems in math, called P versus NP. Essentially, all of modern encryption is a giant bet that factoring prime numbers is in NP, which means we can easily check an answer, but not in P, meaning we can't easily find the answer from scratch. In other words, we're betting that it's easy to check if a key fits a lock, but it's super hard to find the right key just by looking at the lock. If some genius tomorrow proves that P actually equals NP, it would mean a secret shortcut exists for all these hard problems. Our one-way street would suddenly become a two-way superhighway. Every digital lock we rely on, every password, every bank account, every government secret would become completely useless overnight.
And look, this isn't just some abstract theory. It's a very active arms race. The RSA algorithm was our big bet way back in 1977, but by 1994, we learned that a new kind of machine, a quantum computer, could theoretically break our locks with terrifying ease. And that discovery has kicked off a global, high-stakes race to invent new kinds of math that are secure even from the powerful computers of the future.
And that's why all this matters so much. You know, beyond just secure websites, this isn't just about code, it's about power. The laws of math are universal. They don't belong to any single company or any government. They allow us to verify truth without having to trust a central authority, to own our digital identities, and to build systems based on principles that are true for everyone, everywhere. So as we stand on the edge of this new cryptographic frontier, with quantum computers just on the horizon, we face a really critical question. The mathematical principles, they're universal, but how we apply them, that's a choice. The math gives us the tools for freedom and for privacy. Now it's up to all of us to decide how we're going to use them.